Unit 2, pages 34 to 42, Nomenclature. Predicting formulas of ionic compounds. Remember that metal atoms combined with nonmetal atoms make ionic compound. The atoms in the molecule are charged, but all of the positive and negative charges are balanced, so that the net charge is zero. Molecules made with polyatomic ions are also ionic. The empirical formula of table salt is NaCl. The +1 charge on Na is canceled by the -1 charge on the Cl, so that the net charge of the empirical formula is zero. One way to determine the empirical formula of an ionic molecule is to write both ions and their charges. Then cross the charges as in the examples here. The charge on the sodium becomes a subscript of the sulfur atom, and the charge on the sulfur atom becomes a subscript of the sodium. This gives the empirical formula Na2S with an overall charge of 0. And the way that I have taught you in the past is to balance the charges. So if you have a +1 versus a -2, then you need an overall +2 total for sodium, which means we must have 2 sodiums for every 1 sulfide. So Na2S is our formula. Here are some more examples. Here you have ammonium, which has an overall +1 charge, versus sulfide -2. And so this means you need 2 ammoniums to balance out 1 sulfide, which means you're going to put ammonium in parentheses, place the 2 on the outside, and then you have 1 sulfide. Here you have a magnesium with a +2 and a nitrogen with a -3. The common factor of 2 and 3 is 6. So if I have 3 magnesiums at a +2, I'd have an overall +6. If I have 2 nitrogens at a -3 charge, I'll have an overall -6. And so here you have 3 versus 2 to have a balanced formula. Here, magnesium is +2, oxide is -2. Since these already balance, I only need 1 of each in the formula here, and that would be the simplest whole number ratio. Determining ionic charges. Certain ions always have the same charge when they form ionic molecules. The tendency of an ion to have a certain number of electrons arises from the desire of the atom to have a filled shell of electrons. We'll learn more about this in Chapter 6. You want to memorize the charges on the ions in this periodic table specifically here. And notice there are a few transition metals that you'll want to memorize, along with these 3 down here that kind of don't follow the pattern of what we'll have drawn on our note card. For example, magnesium is in column 2A and it will have a charge of +2 when it forms an ion. Oxygen almost always has a -2 charge as an ion. Note, hydrogen is an exception. It can be -1 when it forms hydrides with metals like sodium hydride, and +1 when it combines with nonmetals like HCl. Natural forms of the elements. You should know the common natural forms of these elements, and what's most important is that you recall the 7 diatomics. Start at 7, make a 7, and hydrogen's the 7th element, where these only exist in pairs in their natural state. Naming inorganic compounds. Let's start with organic molecules. They are oil, gasoline, alcohol, plastics, and biomolecules are examples. Molecules made up of primarily carbon, hydrogen, oxygen, nitrogen, and sulfur atoms. What distinguishes organic molecules is the presence of carbon atoms, often bonded together in a chain of atoms. These molecules are extremely important. All of the biological processes that life is based on involve organic molecules. The extensive chemistry of organic molecules is the subject of another course, and we will actually have that as a separate chapter sometime later in the quarter. Inorganic molecules are everything other than organic molecules, which is the focus of this fall and the spring courses. Naming molecular compounds. Recall that molecular compounds result from the combination of 2 or more nonmetal atoms. They can be combined in more than one way, so the name must indicate how many of each type of atom are in the molecule. Here's the procedure for determining the name. Prefixes that indicate the number of atoms in the molecule are listed in the table at left. Here they are: mono, di, tri, tetra, penta, hexa, hepta, octa, and then nona and deca if you go 9 and 10. Okay, so first, is the molecule molecular? If yes, then it contains only nonmetal atoms and contains no polyatomic ions. So the prefix tells you how many plus the element's name, and then you'll follow that with another prefix and the element's name, and then end it with "ide" in order to complete the name of a molecular compound. Note that when the first element has only 1 atom, the mono prefix is dropped. The correct name for NO2, for example, is nitrogen dioxide, not mononitrogen dioxide. Examples of naming molecular compounds. N2O4. For the N atom, the prefix must be 2 or di. The first part of the name is di-nitrogen. For the oxygen, the prefix must be 4 or tetra. The second part of the name is tetroxide. The A on the tetra is dropped to avoid the double vowel AO. So here are some examples of molecules and their molecular names. Dinitrogen tetroxide, dinitrogen monoxide, nitrogen dioxide, sulfur hexafluoride, carbon dioxide, and dichlorine monoxide. Naming ionic compounds. Recall that ionic compounds result from the combination of metal ions with nonmetal ions. Alternatively, one of the ions could be a polyatomic ion. The proportion of atoms in the molecule is fixed and is determined by the charges on the ions. No prefix is needed in the name to specify the number of atoms. No prefix. For many transition metal atoms, the metal can have more than one possible charge. For this course, the most important exceptions to this rule are scandium, nickel, silver, and zinc, which can only be nickel plus 2, silver plus 1, and zinc plus 2. We're not really worried about scandium. Formulas that include transition metal atoms other than silver or zinc must also include the charge, which we represent with a Roman numeral. Here's the procedure for determining the name. Is the molecule ionic? Yes, if it contains both metal and nonmetal atoms or polyatomic ions. Is the metal a transition metal other than nickel, zinc, or silver? Use charge if yes, omit if no. So you would name the metal, and then you would put the charge, if applicable, if it's a transition metal, followed by the nonmetal name ending with "ide." You might have polyatomic ions, in which case the ending would be an "ate" or an "ite" instead of "ide." Silver ion is always Ag plus 1, zinc ion is always zinc plus 2, and nickel ion will be always Ni plus 2. Examples of naming ionic formulas. You have MgCl2, it's going to be magnesium chloride. Notice it's not magnesium dichloride because it's ionic. We do not include prefixes. This will simply be sodium sulfide. This one, we have to be careful because iron is a transition metal that is not silver, zinc, or nickel. So I'm going to have to actually include what is the charge on this ion. So if there is 1 iron to 3 bromides, and bromide on the periodic table has a -1 charge, then 3 of these means I must have an overall +3 to balance it. Therefore, it's iron 3 bromide. Here is silver iodide. Notice I do not need a Roman numeral because silver only has a charge of +1. We have a polyatomic here, ammonium chloride, and then here we have sodium sulfate. Finding the charge on a transition metal. Recall that we learned above how to find the ionic formula when the charges were known. For Fe3+ and chloride -1, the charges are crisscrossed, and the formula must be FeCl3. And if you go with the way that I taught you, I don't teach you to crisscross. I teach you to balance the charges. If that's a +3 and that's a -1, then we must need 3 chlorides for this to be balanced. To work backwards and find the charge on the metal when the formula is known, set up a little algebraic equation. The charges on the ions must sum to the charge on the neutral compound, which equals 0. The charge on the chloride is known. Chloride is in the column of the periodic table where the charges on the ion is always a -1. So here's iron, and we have 3 chlorides, which all have to equal 0. Since each chloride is equal to a -1 charge, then what must be true for this statement? This iron must be a +3 in order to balance out this -3 to make all of this 0. And that's how you can determine it's iron 3 chloride. Finding the compound from the name. Consider the compound name trinitrogen diphosphide. So I know that I have trinitrogen, that's going to be N3, diphosphide, that's going to be P2. The use of tri and di in the name below indicate this is a molecular compound made up of 2 nonmetals. Note the "ide" ending always indicates an element, so you immediately know that phosphide is equal to P. So trinitrogen, tri puts the 3 as a subscript for nitrogen, and diphosphide, di gives me a subscript of 2 for the phosphorus. Consider the compound name iron 2-phosphate. The name does not use mono, di, or tri prefixes, so this must be an ionic compound. The second name does not end in "ide," suggesting that phosphate is a polyatomic ion. Looking up phosphate, in the table of polyatomic ions, we find that phosphate is PO4 with a -3 charge. Use the charges on the ions to find out how many of each ion is in the neutral compound. Crossing the charges gives, so we have iron 2, which is going to be Fe with a +2 charge, combining with phosphate, which is PO4 -3. Remember the common factor of 2 and 3 is 6, so I'm going to need 3 irons and 2 phosphates in order to balance out these charges. Note, +2 times 3 is a +6 overall. -3 times 2 is a -6 overall, and that's going to balance out. And here's your note card for this section. Ionic formulas, you want to determine the positive and negative charges and then balance them. The subscripts are going to be the ratio in the empirical formula. There should be no prefixes, and if you have a transition metal, then it's going to have a Roman numeral to indicate its charge. If you have a molecular compound, there are no charges. You're going to use prefixes, and here's the list of prefixes you should memorize. If it's a diatomic, then it's going to have a 2 subscript, and these are the natural state of these elements when they're neutral. You need to memorize that silver is +1, zinc +2, nickel +2. Also memorize tin 2, lead 2, and bismuth is a +3. And then otherwise, be able to look on the periodic table and note that if something is in group 1, the alkaline metals, it's a +1 charge. Alkaline earth metals, a +2. Group 3 here is a +3. Skip this group 4, and we go to the nitrogen family, which is going to be a -3. And then oxygen family, -2, halogens, -1. Remember that it has a negative charge. It's going to then have a suffix of IDE. So we have nitride, phosphide, oxide, sulfide, selenide, fluoride, chloride, bromide, iodide in this section here.